I forgot that I should mention one thing about yesterday. And hopefully you learned some things or remembered some things about MATLAB and helped develop your intuition about, these kinds of states that we're talking about in 3 dimensions. One thing I realized in talking to Yi-Chen right after class was over is that I made the claim that J, so this is the spherical Bessel function, which is not defined in MATLAB, but I made the statement, so it depends on L, and it's a function of K times R. I made the statement that that was equal to the standard Bessel function with whatever your L is, you had to add 1/2 to it. So that went in as the first, remember, argument there as a function of KR as well. But there's an additional constant that I just thought was part of the normalization, but it's not just a part of the normalization. You also have to divide by the square root of KR. Now that doesn't affect where the zeros of this function are because the zeros are all determined by the numerator. And so our whole process of what K's are going to work is all correct, but this actually changes very slightly what the coloring is of the probability density. So it looks ever so slightly different. This causes this function to fall off a little bit more quickly as a function of R than probably what you saw in there. So just be aware of that. We got all the ideas done that I wanted to do, but and I see my camera's become unfocused again. Sorry about that. Just be aware that, I was typing this stuff in and you guys were following along with me without the stuff in the denominator, but that changes the R dependence. Doesn't change where the zeros are of that function, but it will change what the probability density looks like ever so slightly. I mean, to my eye, they kind of look exactly the same, but we did what we needed to do in terms of learning that stuff. Problems 3 and 4 on the part 1, chapter 4 homework are due Monday? I think Monday. So we'll finish talking about orbital angular momentum today, and certainly at the beginning of class, we'll talk about what you need to know to do those problems. So they're just the next 2, and then you're going to turn in 1 through 4 together, despite the fact that they were assigned at different times. So let me just remind you where we were at the end of Wednesday, because now it seems like a long ways away. We were trying to get actually a differential operator for orbital angular momentum, and we're going to want the x, y, and z hat components of that operator. But we're just taking the definition R cross P, right? And we're writing P in terms of the del operator as a spatial operator, like we did before. And then we're taking the cross product between this. So we're going to get an R hat cross R hat and an R hat cross theta hat. And we thought about stuff like, R hat cross theta hat is going to be phi hat. And R hat cross phi hat is going to be minus theta hat, things like that. And we were able to get the following result that this simplified down to, or at least all the cross products disappear in there, and it simplifies down to this function, these phi hat and theta hat components. For that's step 1. And our next step was, again, we've been talking about LZ and L squared, which is LX squared plus LY squared plus LZ squared. So we really want not the phi hat and theta hat components of this, but the X hat, Y hat, and Z hat components of this. And I think this is where we kind of stopped, or we started thinking about the second problem on that worksheet. How do we write those in terms of I hat, J hat, and K hat, or X hat, Y hat, and Z hat is maybe the way I would prefer to write it now, but same thing. And we thought about some of that geometry. I'm not going to repeat the geometry, but we drew a picture on the board at the end. And we were able to write, what is theta hat in terms of x hat, y hat, and z hat, and spherical coordinate functions. Same thing for phi hat. And then we write those in there, and then we'll get L hat as x hat, y hat, z hat components. And here is the x hat component. Here's the y hat component, and here's the z hat component. Okay, kind of nice. That's where we ended up last time you started working on worksheet 2, and then I sort of just showed how it worked, I think, at the end. Once we have Lx, Ly, and Lz as explicit differential operators, then we can get all the other operators that we formed out of it. So we can get L plus, we can get L minus, just by taking Lx plus ILy and minus. The combination L plus, L minus, and L minus, L plus appeared in 2 ways. We could write L squared, so we can get the L squared operator by taking L plus, L minus. I'm not going to go through this stuff, but it's not too hard to figure out once you formed this, and then you take the product of those things. Plus LZ squared minus H bar LZ hat. So we just showed at some point that this was true, justified that that was true. And therefore, this expression for L squared is an explicit differential spatial operator for the total square of the angular momentum. So we've got L squared and we've got LZ now. And we're ready to write down our differential equations for L squared and LZ. Remember, the idea is these 2 operators commute with each other, and therefore we should be able to find a single collection of eigenfunctions that are simultaneous eigenfunctions of L squared and LZ. And if we do it the old-fashioned way, right, we're just going to write down the differential equations that correspond to those eigenfunction relations and try to solve them. And when we do that, maybe I'll skip this worksheet. It's a little bit confusing, but so we write this down. We say L squared operating on F is an eigenvalue, and for some strange reason, I'm going to write my eigenvalue this way. We've already kind of motivated that, times F back again. And LZ with this differential operator on F is M times H bar times F. When you write those down, so the question that I'm asking in worksheet problem 3 is, if we write out those differential equations, why does Griffiths immediately say it's obvious with no work that those F's are the spherical harmonics? And the answer is that, do I have it written down here? No, I don't. But when you write down L squared on an arbitrary function, f of theta and phi, right? We got derivatives with respect to theta and phi, so my solution would be a function of theta and phi, is equal to this times that function of theta and phi. That is the angular equation we got when we were doing separation of variables in 3 dimensions, and we separated out the radial part, and then we had a leftover angular part, which involved both theta and phi. That was that angular equation for both theta and phi. And then we further separated that into 2 pieces, and this differential equation was the one we got for just the phi dependence in our full product solution. So we're getting the exact same differential equations we got before by separation of variables, which seems a little bit incredible. One way to think about it is that, oops, I've lost control here. One way to think about that is that when we separated variables in spherical coordinates to solve the time-independent Schrodinger equation, we inadvertently, without realizing what we were doing, found, of course, we knew we were finding eigenvalues of H because we were solving the time-independent Schrodinger equation, but we didn't realize that we're also finding simultaneous eigenvalues of L squared and LZ, but now we've just shown that by getting the differential equations that correspond to those operators and writing down their eigenvalue equations. So when we separated variables before, not only did we find eigenfunctions of H, but we also found eigenfunctions of L and LZ, and we found eigenfunctions that are simultaneous eigenfunctions of those. And that means that, without even really checking it, I know if we find simultaneous eigenfunctions, a complete set of simultaneous eigenfunctions for some operators, that means all those operators have to commute. So even though we didn't check it, we're now finding out that the Hamiltonian, which again, we assumed that we had a spherically symmetric potential, it was only a function of R, is going to commute with L squared, and it's also going to commute with LZ. So we already know, just by virtue of separating variables, a whole lot about the eigenfunctions of L squared and LZ. They are our spherical harmonics, and in fact, you can multiply by any function of R times the spherical harmonics, and you would get eigenfunctions of L squared and LZ simultaneous. Okay. Now, once we've solved those differential equations, one of the things that we observed earlier on is that when we separated variables, we need to satisfy some spatial boundary conditions on theta and phi. What happens as a function of phi as you go between 0 and 2 pi? It better be doing the same thing at 0 as it is at 2 pi, right? What's happening as a function of theta? It better be continuous at theta equals 0 and at theta equals pi, where the coordinate system kind of has a little bit of a strange singularity there. And those are what gave us the requirements on what the allowed values of L and M are for those spherical harmonics. L had to be an integer only, and then M goes from minus L to L in integer steps. Okay. We're now finding, or at least recently when we did the algebraic solution, we found more generally it was possible to have allowed values of L that were half odd integers, 1 divided by 2, 3 divided by 2, 5 divided by 2, which don't satisfy the requirements for the boundary conditions up there, okay? But as you know from your work in modern physics, these, even though we won't allow these circled half-odd integer L values for spatial wave functions. So if we're finding a spatial wave function that represents orbital angular momentum definite states, that those values won't be allowed, but they are of interest in spin, which you're reading about in section 4. Maybe you read about. I don't know that we'll get to section 4. Hopefully we'll finish talking about angular momentum today. We're at the conclusion, but I wanted to work on that worksheet that is part of the homework. And in fact, here we are. Any questions on the upshot of that? So we already know what functions of theta and phi and R are functions, are eigenfunctions of L squared and LZ simultaneously, because we've already done the work. We didn't realize we were doing the work back when we separated variables, but we were. Okay. Remember our worksheet where we were thinking about this strange combination of states, which was psi at time t equals 0 for a hydrogen atom. So we're saying I can look at, remember R's subscripts are L then M, and Y's subscript is L and the superscript is M. So we're seeing a linear combination of 3 different states. And now I know that the subscript and superscript on the Y are telling me about a state of definite angular momentum. So this is a linear combination of 3 different states of different angular momentum, right? And we did the first page there where we weren't really thinking about angular momentum. Now I want you to look at the second page and the third page and spend a little bit of time working on them. So again, we found that constant C to be the square root of 4/6, which is 2 over root 6. That constant C that's shown at the top, we've already solved for it. There's some questions about what possibilities there are when you measure L squared and LZ and what the corresponding probabilities are. See if you can think about E, F, and G, and maybe we can think through H together, which is the third page. Again, if you're on Zoom, that's posted under today's date. It's also posted as homework, which is part 2 of the chapter 4 homework, but you can, if you're filling this out in class, you can just write it out neatly and then turn it in when it's all finished. Okay, just to kickstart us on this, by looking at the state at the top of the second page, which is the same as the one at the top of the first page, what quantum numbers, little l, are we talking about here? Script L. I heard someone say 0 and 1 and 2. Yes. So I'm looking at either the second R subscript or the subscript on the Y, and I see a Y subscript 0, Y subscript 1, and Y subscript 2. So we're talking about those L values. How do this is the quantum number that determines the total angular momentum squared. So if I ask for the values, if we measure the square of the total angular momentum, what value would correspond to little l equals 0? Well, it is 0. So how, in general, if I told you this quantum number is script L, what would be the formula in terms of that? L times L plus 1 times h bar squared. I know there's a lot of details in here. So I've got the allowed values of L squared, the ones that we have only non-zero probabilities for, are going to be 0 times 0 plus 1 times h bar squared. That's just 0, right? 1 times 1 plus 1 h bar squared, or 2h bar squared. And 2 times 2 plus 1, 2 times 3 is 6h bar squared. So the allowed, the possible outcomes of the measurement of measuring the square of angular momentum, seems to make more sense to say you just measure the angular momentum. However we do that, I don't have a good answer to that question. But if you measured the orbital angular momentum, you would get the square root of this number. And we get those three possibilities. And what are the probabilities that are associated with them? What do I look at to get the corresponding probabilities? So I would say I get possibility of 0 h bar squared. I think we said 2 h bar squared or 6 h bar squared. And what are the corresponding probabilities? Are they all equally probable? Yeah, it's the coefficient squared in the expansion, right? It's just like the idea that, way back when we were talking about one-dimensional things, we would say psi of x at t equals 0 if we write it as a linear combination of states of definite energy. These coefficients, magnitude squared, tell us the corresponding probabilities. Now we're writing psi of r, theta, and phi at time t equals 0 as a linear combination. Well, I ran out of space here. This is going to be a big expression. A sum, and I forget to unshare this for the sake of the video. We're writing this as a sum of RNL YLMs, right? Of course, this is a function of R, this is a function of theta and phi, with different coefficients. We have a different coefficient for every N, L, and M. So we have to sum over all the allowed values of N, L, and M. And the magnitude squared of those coefficients are the probabilities, just like they were before. Now, it turns out in our expansion, we know this expansion. Our expansion is given at the top of the page, and there are only 3 non-zero terms. All the other C's are 0. And so those remaining coefficients, magnitude squared, are the probabilities. So if we look at them, I've got a 1 over root 6 corresponding to L equals 0. So that means the magnitude squared is probability 1/6. It was the same thing for L equals 1, right? 1/6. And then for L equals 2, that's the one we found. That would be 4/6, 2/3. And of course, they add to 1. If we measure a physical quantity, we have to get one of the 3 values that are the only possibilities. Okay, try it for LZ now and answer G as well. Okay, what are the allowed values of LZ if we're in this state? What are the non-zero probability kind of values? Right, M equals 0 or M equals 1. And what does that mean in terms of actual values of LZ? Yeah, 0 H bar or 1 H bar, right? It's M H bar that are the allowed LZ values, right? So we have 0 H bar or 1 H bar. And how do we calculate the probabilities associated with those? Well, the 0 is pretty clearly 1/6. What about 1 H bar? Well, I have to add together all the probabilities that are consistent with M equals 1, right? So that's 1/6 plus 4/6, which is 5/6. So if I measure LZ, I get H bar 5 out of 6 of the times and 0 1 out of 6 of the times if I do it a whole bunch of times on an ensemble of identically prepared systems, all in this state. Okay, questions on that? Just, I know we're not doing, well, this isn't terribly complicated, but part of it is just disentangling all the notation in your mind, right? And getting familiar with it. Does your answer depend on time? This was true at time t equals 0. Why doesn't it depend on time? Does the state itself depend on time? Yeah, the state does depend on time. We do the same thing we've always been doing to put in the time dependence. In each one of these terms, which we've already justified by separation of variables, each one of these terms is a state of definite energy, as well as a state of definite angular momentum squared, and a state of definite LZ. So we just put in the corresponding factor e to the minus I ENT over H bar, where we look at the n value that's in that term and we get the corresponding En, the minus 13.6 EV over n squared for the hydrogen atom. We're talking about hydrogen states here. So this state does depend on time, but the magnitude squared of the coefficients, when we put these things together, sometimes we might say, well, this is what it was at time t equals 0. This is CNLM as a function of time. Those coefficients have some time dependence, right? The expansion in terms of these functions is going to have different coefficients at different times. Those depend on time, but if we take the magnitude squared, the complex exponential part goes away. And so the probabilities don't depend on time. And that's what we're asked about for our answers here. We were asked about probabilities, so those don't change. All right, any questions on page 2 there? Okay. Good. Let's go on to page 3, and I might have you think through some of the later parts, but I wanted to talk about H, the first part of H together. So again, same state that we've been talking about, same C that we already figured out in there on the 3rd page. Write a properly normalized wave function. Okay, so I forgot to read the first sentence. Suppose you start out in that state at time t equals 0. And we measure at time t equals 0 LZ and find a value of plus H bar. So we got what, the odds were with us that we would find that. So we measure LZ and we find plus H bar. Write a properly normalized wave function for the particle immediately after this measurement. Well, what are we to do? There are kind of 2 states. And in this case, that are that are part of the original wave function that are consistent with this measurement, right? This probability came from kind of adding 2 probabilities together. And this is a little bit of a weakness in the way Griffiths presents the generalized statistical interpretation. Back in chapter 3, he says, when you measure something, the state collapses to the corresponding eigenstate. Well, in this case, we're measuring something, and there's more than one eigenstate that it might collapse to associated with this. And maybe, for all I know, maybe you guys talked about something like this in modern physics. I'm not really sure how much depth you go into. Anybody have an idea what to do? In other words, if I have my psi at time t equals 0 is a sum of 3 terms. And I make a measurement which is inconsistent with this term, but 2 of the terms are left. Do you have any idea what we're supposed to do? This really isn't covered by the words that Griffiths writes down in chapter 3, but there is something that you should do in this case. You keep both of them and you just renormalize it. So instead of saying that it collapses to the corresponding eigenstate, that's what, I went back and looked it up. That's what Griffiths says in words. In this case, there's more than one eigenstate, and you might have different coefficients in front of it. What you really do is you project on to the part of your state that you're in that's consistent with the measurement, and then renormalize, of course, to get a new normalized state. So in this case, the first part goes away. It has m equals 0, but we had, before we normalize, we had a root 1 over 6 r21 y11, and then a root 4/6 r32 y21. Now that state, if I throw this first part away, is not normalized anymore, right? Because the sum of the coefficients have to add up to 1. So, there are various ways you can think about it, but the easiest way to think about it is, well, okay, that's my state. It's just not normalized. So let me put a constant out in front. And let me require that when I take the magnitude squared of this state, and integrate over all space, I get 1. And use the fact that lots of these functions are orthogonal to each other, right? Are these both y11? Yeah, both y11. No, this one's y21. I miswrote that one down. Just didn't look familiar. So, of course, y11 is orthogonal to y21. And so when I take the magnitude squared of this and integrate over all space, the one that corresponds to this star times this will give 0 when I integrate over all space. And this one star times this will give 0. It's only the magnitude of this one squared, which will integrate to 1, accepting this thing, right? We're already saying these were already normalized. We're assuming those symbols represent normalized functions of r and theta and phi. So this is normalized. So if this is our psi at time t equals 0, let me calculate the magnitude of psi squared and integrate over all space. I'm just going to be a little bit sketchy. So, d tau for a volume element. That's going to give me the magnitude of a squared times, when I do this, I'm going to get the inner product of this star times this, which is 0, this star times this, which is 0, this star times this, which integrates to 1, except for this factor. So I'll get a 1 over 6 times something that integrates to 1, plus this one squared, and this part integrates to 1. So I'll get a 4/6 times 1 after I integrate over all space. Okay? And now I'm going to demand, I don't know, we need a symbol that says I'm going to demand, or I'm going to, assert that this is going to be equal to 1. I want that to be equal to 1, and now let's solve for what a squared has to be, or what a has to be, right? So this is 1/6 plus 4/6 is 5/6, and when I invert that onto the other side, I get 6/5, and then I take the square root. So that means a is equal to root 6/5. And so that means, I could put in a root 6/5 there and a root 6/5 there. And of course, the 6's cancel out there. So the new coefficients are root 1/5 and root 4/5, which, adds up. I'm expecting the squares of those coefficients to add to 1, so it's definitely normalized, right? I get a probability of 1/5 and a probability of 4/5 when I square those coefficients. Okay, so my answer to, after all that work to the first question in part H, that very top part, should be root 1/5 times this plus root 4/5 times this. All right. Why don't you guys go ahead and think about answering the rest of these questions on here. A lot of them are just, interpretations. But that was something that was kind of new, I feel like, because when we took a measurement before, it always collapsed to a single eigenstate of something. But now we've got multiple eigenstates that are consistent with the measurement. So we really have to kind of just throw away the parts of the wave function that are inconsistent with the measurement and renormalize. That's our updated version of the generalized statistical interpretation. It's going to be really nice in fall when we're not spaced apart, for those of you who are still here. And I can actually force you to get in groups and actually talk to each other. That is one thing I miss. And by the way, if you found my argument too sketchy here, I really want you to write out the details, right? If we just throw away the first term and you buy that, and then we put an A in front of it, calculate this. Just do it and try to convince yourself that when you take the magnitude squared of this, of course, I'll get 4 terms. 2 of them are going to give 0. Why? Think about that. Okay, well, most of you have done the first couple of them. Maybe we can just go through them together here, or I can ask you at least on the first couple of them, because it seems like most of you have thought about those. Riley, what do you say about the second question, which is in part H? Is the total angular momentum well defined? Why or why not? After this measurement that's made it sort of collapse to the state, it really projected out the part that was inconsistent with the measurement. So we've got the quantum numbers encoded in here. What quantum number tells us about the total angular momentum, or what we've been talking about is the square of the total angular momentum? If I know the square, I know the total, right? That's just the square root of that. What quantum number, n or l or m, tells us how to compute this thing? L does, right? Remember, it was L times L plus 1 h bar squared, right? So that means I'm looking at little l here. Okay, so the question, is the total angular momentum well defined? That means, is there only one possible outcome for a measurement of L or L squared? No, there's not, because this is L, the subscript of y. L equals 1 and L equals 2. Little l equals 1 or 2. That quantum number can be 1 or 2. And that means L squared could be either 2h bar squared or 6h bar squared, as we determined before. We threw away the 0 one, but we would say it's not well defined. In the same way that if you're in a linear combination of two definite energy states, you wouldn't say that the energy is well defined. The expectation value of energy is still well defined, but you wouldn't say the energy is well defined because there's more than one possible outcome of an experiment. That's just the way we use the words well defined. It means it's well defined if there's only one possibility when you measure that thing. Jake Woosley, what about the z component of angular momentum when we're in this state that we sort of collapsed to after the measurement that's suggested? Is the z component of angular momentum well defined? So what do I look like? What quantum number? For total angular momentum, we were looking at the quantum number L. For LZ, to see what outcome we would get for if we were in this state or this state, what quantum number do we look for there? The N, the L, or the M? It's the M in this case, right? These are M h bar. So the eigenvalues of LZ are integer multiples of h bar. Well, at least in the case of orbital angular momentum, they're integer multiples. So we're seeing in here, and you got to, part of this is forcing you to look at these subscripts over and over again. So you just remember, this is M and this is M, right? It's Y, L, M. We always say the subscript first for whatever reason. Usually when it's typeset, the subscript's a little bit to the left of the superscript. So this is M, there's only one value of M, and that means if I measure LZ, M is definitely 1, and the value I'll get is 1 h bar. So yes, it's well defined. Well defined means, are we in a state where there's only one possibility when we measure that thing? Only one possibility with a non-zero probability. Okay. What do you say? Maybe I won't call anyone specific for this because it's sort of a weird question. Is the state of your particle well defined after that measurement? Suppose that we were back in chapter 2 and I said, we're talking about maybe a free particle, right? So potential is 0 everywhere. And at time t equals 0, my particle is in this state, some sort of Gaussian state. We'll normalize it, right? A is just to normalize it. Is the state of my particle well defined? Is there any information that you're lacking about it? Like when we say well defined, we mean, is there something more that you could know about this state that I'm not telling you other than the normalization? We'll assume we found the normalization. No, it's in a definite state. There's no uncertainty about the state that it's in. Now, this isn't a state of definite energy, and it's not a state of definite momentum, right? It's not a state of definite kinetic energy, but it's still a definite state, right? I'm not saying, well, it could be in one of these two states. In the same way, this is a definite state. This is sort of analogous to saying, well, maybe my psi at time t equals 0 is just a sum of two definite energy eigenfunctions. Psi1 of x plus psi2 of x. And if we wanted to normalize it, maybe we could put equal coefficients in front of it to make it normalized, right? If I said at time t equals 0, I'm in a linear combination of the first excited state and the second excited state, let's say. Suppose we're talking about harmonic oscillator kinds of states, right? If you're in a linear combination of the first excited state and the second excited state of the harmonic oscillator, that's a perfectly definite state. There's no more information I could give you about what the particle is in at that time. As opposed to, here if I said, oh, we're talking about a hydrogen atom and the L squared eigenvalue is corresponding to little l equals 3. Well, that doesn't determine a definite state, right? There are lots of these kinds of functions I could write down that have a 3 down there, right? And I've only told you a partial description. That wouldn't be a definite state. But if I say my particle is in this state, there's no more information I could give to you about it. So it is in a definite state. It's sort of a strange question. Obviously, I photocopied this from somebody else or stole it from somebody else's course, but I thought they were good questions. They raise a lot of things that you may not think about after going through Griffiths. It's a definite state. It's just not a state of definite L squared, right? Suppose, and it's also not a state of definite energy, because I can look at the end, that's something that hasn't even been asked about yet. Maybe it was asked on the first page, but look, the energies are n equals 2 and n equals 3, so it's not a state of definite energy either. But it is a definite state. It's just not a state of definite energy or a well-defined particle state. The next part says, suppose you take the state you formed above, and then you measured L squared and found a value of 6 h bar squared. Now, what's the normalized state of this hydrogen electron? So here was the state that we were in after the description at the top of part H. And now we measure L squared and we get 6 h bar squared. What do we do to this to get our new state? Yes, this is the one that corresponds to L squared equals 6 h bar squared, right? This is little l equals 2, and the eigenvalue we're talking about is L times L plus 1 times h bar squared. If we put in 2 times 2 plus 1, that's 6 h bar squared. This part's inconsistent with it, so we, again, throw away that part and renormalize just this part. But we know how to normalize that because we're already assuming these symbols correspond to normalized wave functions. So the appropriate coefficient now in part I is 1, because those are all that one state is already normalized. We don't have a linear combination of those different states. So psi is just R32, Y21. Has this final measurement affected the z component of angular momentum? No, it hasn't, because we found out that both of these terms were consistent with m equals 1, right? We threw away one of them. It's still in a state of definite z angular momentum, so no. One way to think about it is, a different way to say the same thing is that the operators for L squared and LZ are compatible with each other. So if they commute with each other. We showed that earlier on. So if I measure L squared, it doesn't affect the values of LZ. If I'm in a state of definite LZ and then I measure L squared, it had an effect on the wave function, but it doesn't have an effect on the LZ probabilities because those two operators are compatible. So they commute with each other, and that means the measurement of one doesn't disturb the probabilities associated with the other. Last question, at least for this page. The next part has to do with spin of this. We haven't introduced spin into the picture yet. At this moment, suppose you made a measurement of the x component of angular momentum. We've been talking about z components of angular momentum, but now we're going to switch to x components. And the question is, what are the possible values you might obtain? So I think the implication is we're in this state. So we know the energy, we know the total angular momentum, squared or unsquared, and the z component of the angular momentum. But now we're going to measure Lx. What are the possible outcomes of an Lx measurement? We know that the possible outcome for an Lz measurement is just 1 h bar, right? But if we switch our axis and decide to measure the component of angular momentum along the x direction, what are the possibilities here? You know, we can't necessarily look at these eigenvalues and know the associated probabilities, and we'll talk about how to think about that later on. But for right now, the important thing is that when we measure, you know, Lx, Ly, and Lz all commute with L squared. That means if I measure, just like when we measure Lz, it doesn't mesh up L squared. If we measure L squared, it doesn't mess up Lz because those two operators commute. It's the same way with Lx and L squared. Lx does not commute with Lz, but it does commute with L squared. And so when I measure Lx, I'm still going to get a state with L squared that is equal to 6 h bar squared, corresponding to little l equals 2, because I'm measuring something that is compatible with L squared. Right? So maybe to write it out, since L squared as an operator commutes with Lx, that commutator is 0. That means that if I measure Lx, it doesn't mess up the probabilities associated with L squared. And we've got a definite state of L squared, right? So before we make this measurement of Lx, we were in a state of definite L squared of 6 h bar squared. After we measure Lx, we're still going to be in a state of definite L squared is equal to 6 h bar squared, or little l is still going to be 2. So if all we know is that little l equals 2, what are the possible values for Lx? Well, it's everything from -2 up to 2. It's the same way it works for Lz, right? Lz is, there's nothing special about z, could be calling it x. So if L is still equals 2, the possible values for Lx are -2 h bar, -1 h bar, 0 h bar, 1 h bar, and 2 h bar, right? M goes from -L to L, and it's m h bar that gives the value of Lx or Ly or Lz in this case. Now, it's a different question to say, what are the probabilities associated with this? And you're told in bold font or, you know, all capitals or something that you do not need to find the corresponding probabilities. So that's okay. But these are the only possibilities. For sure, if there's going to be non-zero probabilities, these are the only ones that can be in the list. All right, any questions on those 2 pages, which you should write up, you know, neatly and to your satisfaction? If I left out some details here, make sure you write enough to feel satisfied with the answers. All right, let's go back to the slides and see where we're at here. I think that's probably it. Oh, these were a couple reading response questions that were from section 4.3, but had to do with spin, you know, and you've read about spin probably now. We'll just barely start mentioning it today, but is spin anything more than intrinsic angular momentum? This may not be answerable, but what causes this intrinsic spin then? Is there any importance to the spin except that it explains why 2 different energy states arise from the same NLM values, one spin up and another spin down? I guess the perspective is whether you're saying our whole world is non-relativistic quantum mechanics, or if we're asking this from the perspective of the real world, spin does make a huge difference, and it's not just the number of states consistent with certain orbital angular momentum, there being two linearly independent states for an electron. And that is because when particles decay or transmute into each other, which is not allowed in non-relativistic quantum mechanics, which is the subject of this course, right? You can't have, there's no description that we're ever going to find in non-relativistic quantum mechanics of, a muon decaying into an electron and emitting, a neutrino onto it or something like that. But when you have particles that are decaying, or if you smash two particles together and different particles come out, sometimes the spin angular momentum, so I might have a particle of non-zero spin angular momentum that decays into a pair of particles of zero spin angular momentum, which might sound superficially like angular momentum is not conserved, but it is conserved. Their spin angular momentum might be zero for each of those particles, but they're in a state of non-zero orbital angular momentum. So when there's decays or things like that, it's not that spin angular momentum and orbital angular momentum are separately conserved, but that the total angular momentum has to be conserved. And so spin isn't just something that tells us the number of states, and it's not immutable. Once we allow particles to transform into each other, which we know happens in the real world all the time, especially in collider experiments, but also in nuclear decays and things like that. So I would say no, the answer is it's not much more than that, although in non-relativistic quantum mechanics, it's perhaps not so exciting, because once you're a spin 1/2 electron, you're always a spin 1/2 electron, and none of that spin can get converted into anything else. And so it's sort of like a whole world that's separate from the spatial wave function stuff when we're talking about spin. But fundamentally, once you allow transmutation, that happens in quantum field theory. That if you go to graduate school, hopefully you get a chance to take an advanced, a quantum field theory introduction class where you're doing those Feynman diagrams and things like that. You'll learn about how these conservation laws play into that, and these two types of angular momentum can transmute into each other. Let's see this was also about spin down here. How do we define spin as an intrinsic angular momentum if there's no classical analog to compare it to? That's right, we can't really think about, well, even for orbital angular momentum, we still can't think of spinning mass, right? And we're talking about wave functions here. So our intuition about what it means has already broken down, but the claim is here that it's even more broken down than usual. We shouldn't be thinking of any spatial kind of thing at all. Would it be appropriate to call spin a different type of angular momentum? If so, does spin, like the classical angular momentum, require two dimensions to give a meaningful interpretation to, and how was this determined? Yeah, I mean, that's a good question. In other words, since it doesn't have anything to do with space, could we have had a spin 1/2 particle that lived in one dimension? And I think probably nobody knows the answer to that, or if they do, it's above anything I've ever learned about. There may be some weird result in quantum field theory that tells you relations between number of dimensions you live in spatially and what spin states are allowed. I don't know about anything about that, but it's sort of, in principle, yeah, a spin, in a particle that lives in a one-dimensional line, like we were talking about in chapter 2, could have spin states. But we know if we think of them as associated with spatial states, and classical angular momentum as r cross p, there's no sense to it in one dimension, right? If you think of a top can't exist in one dimension, right? Because there's no perpendicular direction for things to be moving around. And more generally, in terms of r cross p, in two dimensions, I could say, here's my origin, here's where my particle is, and it's moving with p in this direction. So there's my r, and r cross p in this case would go into the board. But if you're in one dimension, here's my origin, here's r, p can only be in that direction. When I take the cross product between parallel or anti-parallel vectors, I always get 0. So it doesn't seem to make any, sensible thing to define there if you're always going to get 0 for r cross p. Nonetheless, it seems like it's in principle allowed, but who knows? We are stuck in 3 dimensions, and spin is here in this world. We can't experimentally probe one-dimensional worlds. Ooh, 139. Okay, well, we better close it up here. We're going to start talking about spin. And we already did talk about it a little bit at the end of section 2, I think, when we were talking about matrix elements, but we're going to elaborate quite a bit more. So Griffiths says something to the effect that spin angular momentum of a rigid body is, in classical mechanics, is no different in principle from orbital angular momentum. In other words, a top, which we could say is sort of what we think of when we think of electron spin, if you're thinking about anything at all, right? We've got this ball of mass and charge, which is an electron, and it's spinning. So that gives you a magnetic moment because the charge is circulating around, but it also gives you orbital angular, or gives you spin angular momentum because you've got mass going in a circle. At least that's the best picture we have. In quantum mechanics, they're really different from each other. I mean, they're the same kind of quantity. They have the same units, and we know in the real world they can transmute into each other. So spin can change into orbital, orbital can change into spin, and it's only the total that is conserved. And yet we'll find out that the boundary conditions, or we've already mentioned that the boundary conditions that limit the types of orbital angular momentum you can have don't apply to spin. And so we can have states of spin corresponding to not little l equals 1/2, but we're going to call it little s equals 1/2. So the values that are allowed there are different. And there's no way to spatially think about it. Now, does that mean that it's unrelated to space? You know, people will say it's an internal property of the particle. Internal just usually means a non-spatial property. Who knows? I mean, it seems ridiculous that we can think of something that's happening spatially, and then there would be a quantity that can be transmuted into it that has nothing to do with space. I guess the best answer probably is that we don't know what happens when you examine space at smaller and smaller and smaller scales, right? We tend to think of it as always continuous, no matter how much you zoom in. But as you know, in the search for quantum gravity, people think that, you know, maybe space-time becomes discrete at some point, or it has a really weird structure that you never would have imagined. And so the usual boundary conditions that limited little l to integer values at large spatial scales, and by large, I mean, you know, maybe the atomic scale. Maybe at really small scales, that doesn't apply anymore because space becomes really weird in some way, and therefore we have more allowed quantum numbers. But they're really the same kind of thing. One's happening at a small scale where the same restrictions don't apply, and one's happening at a large scale where some effective restrictions apply. So in any case, we're going to start accepting half-odd integer values of this, and we're going to use different quantum numbers, s and m sub s, rather than l and m. All right.